Hey Vsauce, Michael here, and I'm sure that we all love to have fun with hand shadows. But how much does a shadow weigh? It might sound like a silly question, because it is. I mean, a shadow cannot be put on a scale and weighed, but the material that it falls on top of can be weighed. And we know that light has energy. In fact, when light encounters an object, it pushes that object just a little bit. On the surface of Earth, when sunlight is hitting it, every square inch is being pushed with a force of about a billionth of a pound, which is basically nothing. But over a large enough surface area, the results can be pretty fun. On a sunny day, the city of Chicago weighs 300 pounds more, simply because sunlight is falling on it, pushing it. In outer space, where solar wind isn't filtered by Earth's atmosphere or magnetic field, the results are even bigger. A spacecraft traveling from Earth to Mars would be pushed by light 1,000 kilometers off course. So these things have to be factored into journeys to Mars. We've actually already created things that can sail with light, giant reflective solar sails that are pushed by the sun's light. So in a way that is calculatable, though difficult to measure, an area covered in shadow technically weighs less than surrounding areas being pushed by light. But enough about the sun. There are 3 astronomical bodies that can cast shadows on the surface of Earth bright enough for us humans to see. One is obviously the sun, and the other is the moon. But what's the third? Venus. Pete Lawrence investigated this over at Digital Sky. Now, to make sure that the shadow he saw was caused by Venus, he used a tube that could be pointed at specific regions in the sky. Inside the tube, he put a cutout shaped like the astronomical symbol for Venus. Now, here is light coming through the tube when pointed just adjacent to Venus, at a point in the sky relatively dark and empty to the human eye. But here is what came out of the tube when pointed at Venus: a Venusian shadow. We all know that light travels quickly, 299,792,458 meters per second. C. But this light right here, in fact, the light coming off of your screen into your eyeballs right now, is moving slightly slower than C. Because c is the speed of light in a vacuum, but all of this light is having to travel through a medium, in this case air. The speed of light in air is ever so slightly slower than c, 298,925,574 meters per second. This is interesting because light travels more slowly through different materials, but c remains the universal speed limit. And as long as an object doesn't go that fast, it can still outpace light in a material. A charged particle, for instance an electron, can travel through water faster than light does, but never faster than c. When this happens, we get something analogous to a sonic boom. We get a photonic boom. In a sonic boom, the sound information propagating off of the object is in the form of compression waves, and as the object gets closer and closer to the speed of sound, the speed that those waves are moving away from it at, each new wave has less time to get out of the way of the next, until eventually the waves collapse all into each other and the density and pressure is enormous, causing a sonic boom. Normally, when a charged particle moves through a material whose molecules can be polarized, the molecules give off photons, but each photon has room to fly away, and the waves all destructively interfere with each other, so no radiation is given off. But the faster the particle goes, the less room the photons have away from each other, and their waves begin to constructively interfere, giving off a photonic boom, Cherenkov radiation. Astronauts, especially those who have gone all the way to the moon, have reported seeing flashes of light. Many people attribute this to high-speed particles moving through the liquid inside their eye faster than light normally would, causing photonic booms right inside their body. Speaking of the speed of light, here's a great question a few of you have sent me. It involves a possible way of going faster than C. Here's how it goes. Let's say I want to push a button that is a light year away from me, which means that it would take light, the fastest possible thing in the universe, a year just to get from me to the button. Okay, well, what if I built a board 1 light year long, all the way from me to the button, and then I pushed one end of the board? Would the other end immediately push the button? And if so, did I just break the speed of light? Did I just send information faster than light? Well, we're not talking about the speed of light anymore, are we? We are talking about the speed of push. When you push a rigid object, what you are really doing is putting a series of compression waves through the object, which move at the speed of sound in the object's material. The information about, whoa, we've been pushed, you should move, is sent via that compression wave, and it only travels at the speed of sound. So when pushing a normal day-to-day size type object, it feels almost instantaneous. But when pushing a light-year-long board, it would take a lot longer. A cool way to see this in action is to look at an object in which compression waves travel more slowly. For instance, what VSAUCE has done blowing minds by showing slinkies being dropped. The information telling the slinky that, hey, we're moving, travels through the slinky slow enough that a slow-mo camera can see it happen. If you haven't watched all of VSAUCE's slinky videos, you've missed out. In fact, you should watch all of their stuff. It is superb. But to wrap things up, here's the point. The speed of push is not instant, and it's certainly not the speed of light. But light can push you. In fact, technically, you weigh more when the lights are on than you do when the lights are off. I've put links in the description to all kinds of cool things you should definitely check out for fun and for science, and as always, thanks for watching.